Hello everyone, welcome to a video series that I hope I don't drop after like 3 attempts, like my last one. But anyway, in this series we're going to discuss a topic that is very near and dear to me, quantum mechanics. What is quantum mechanics? In the most general sense, it's the study of the movement and energy of the very small, of atoms and the particles that compose them. Quantum mechanics remains an integral component of modern research and technological development. Without it, we wouldn't have nuclear power plants, which provide clean energy to millions of people worldwide, nor would we understand why things have mass, thanks to the amazing research done at the CERN laboratory in Geneva, Switzerland. Before we dive into the material, I want to acknowledge the sources I'll be using to supplement this series. First of all, an introduction to quantum mechanics by Griffiths, both the second and third editions, volume 3 of the Feynman lectures, which are available online in print, and I believe the online version is for free, and I will be linking that in the description below, along with Fitzgerald's Thermodynamics and Statistical Mechanics, older editions of which are also available online for free, and I will also link in the description below. So if you wish to read and flip through those books themselves, feel free to do so. They are great texts if you want to really get into the meat of the material. Now, when you're introduced to quantum mechanics, you typically need some basic understanding of the mathematics involved. Specifically, you need to know a bit of integral and derivative calculus, some linear algebra, some probability theory, and just a little bit about ordinary and partial differential equations. In fact, depending on the version that you're using, you're going to encounter operations from these branches of mathematics quite literally immediately. For instance, the equation that Griffiths first presents is the Schrödinger equation, which reads the complex number I times the constant h bar times the partial derivative with respect to t of our wave function is equal to the negative quantity of h bar squared divided by twice the mass of our object times the second partial derivative of our wave function with respect to x plus our potential energy V multiplied by our wave function. In this equation, our Greek letter psi represents the wave function of the particle. It is a multivariable function, typically, that describes the particle's position with respect to its location and its time, x and t. There's one major caveat, however. We cannot say that for an exact coordinate domain, x, t, the particle is at an exact location at that specific time. This is due to something called the Heisenberg uncertainty principle. We'll derive it or discuss it a little bit later, but for now, just think of it like this. The more we know about the position of the wave, we know less about the actual wave itself. So if we know that this particular wave exists at this very particular point, we can't induce other qualities about that wave, like its wavelength. I'll get to that in a minute once we talk about uncertainty, but at that point it will become a little bit more clear as to what I'm trying to tell you and visualize, right? But anyway, consequently, we must consider the wave function as a particular kind of function, a probability density function. A probability density function is a special type of function that maps variables from the domain to values in the codomain in between 0 and 1. These values essentially represent the probability of finding our wave between two specific points. Mathematically, this means you're more likely to find a particle in a certain region of space rather than at a single point. In fact, we consider the entire domain of all possible space. The probability of finding our particle is 100%, right? Makes sense. If you look throughout the entire universe, you're going to find the one thing you're looking for. It quite literally just has to be there, axiomatically, right? We represent this idea with an integral, where we square the absolute value of the wave function and integrate it from negative infinity to positive infinity. When we do this, it gives us a probability of just 1, right? So you'll have a 100% chance of finding the thing you look for if you look through literally everywhere just to find it. Don't worry about the fact that we're squaring it at this moment in time. We're going to get to that in a minute too. Griffiths really likes to jump around. But when we think about this in terms of what it means to have location described as a probability rather than a concrete, yes, it's there, no, it's not, we kind of have to think about the philosophy of physics a little bit. Namely, we kind of have two branches or two interpretations that we can actually look at this equation and deduce from it, right? The first of which is the less accepted opinion regarding quantum mechanics, and it's largely because it wouldn't work. This interpretation goes essentially as follows. When we make a measurement about the particle, it was already existing in that position. That would make sense for macroscopic particles or molecules or anything that is big enough to grab with your hand, think about your glasses. If you leave your glasses on a coffee table, you leave the house for a couple of hours, and then you come back home, your glasses, unless you have a really rowdy cat, more than likely haven't moved a single inch. However, because we're not dealing with macroscopic objects, we're dealing with waves here, this really isn't the case. So if a particle has assumed some position, we wouldn't be able to make estimations about its other properties, like I said earlier, and vice versa. As a result, we couldn't use this current statistical model with the probability density approach that forms literally the foundation of quantum mechanics, and the entire field itself would fall apart. We wouldn't have Q&M without probability, and we need probability to talk about things we aren't 100% sure about. Makes sense. Consequently, we get something called the Copenhagen Interpretation, which is the more accepted interpretation. It goes as follows. Now, it's a little bit weird to think about, but before we make any sort of observation, we can't exactly say that the particle was anywhere at all, but rather that the act of observation itself caused the particle to behave a certain way. Here, the act of observation can be considered an experiment, right? And experiments always influence the variables at hand. In technical terms, when we observe a particle, its wave function collapses, and it assumes a specific quantum state and location. This view is supported by repeated testing and allows us to continue using the statistical interpretation of the wave function. What's really fun about this, in terms of the repeated experimentation, is that once we observe a particle in a certain position of a certain ensemble of particles, it's going to stay there, regardless of how many other observations we make on that particular ensemble. It's a little bit freaky, but it shows us that now that out of all of the probable cases that it could have assumed, it's just choosing to take that one there. That's what we mean when we say that a wave function collapses. Now that we have a little bit of the philosophy of quantum mechanics out of the way, we can actually do some math, right? We need a little bit of math, obviously, before we actually start analyzing wave functions. First, we need to discuss the concept of an expectation value. For a discrete variable, so like big numbers, 1, 2, 3, 4, 5, 6, whole numbers more specifically, the expectation value is essentially just an average. So for a variable j, we can say that its expectation value is equal to the sum of I equals 0 to n of j sub I times the probability of p sub I, which is where j obviously is the random variable discussed at hand, and pi is the probability associated with each term ji in an ensemble. So you take all of your ji's, you multiply them by their associated pi's, and then you take each of their respective products and you sum them all together. An easier way to think about this is the good old add everything up and divide by how many terms you have approach. This sum can be rewritten essentially as 1 divided by n times the sum of j to whatever of j times the number of j's, where nj obviously in this equation represents the number of j's occurring in our sample space or our ensemble, and n is the total number of elements in our sample space. Makes sense, it's an average. We can extrapolate this for functions by replacing the discrete random variable with an entire function. So if we wanted to find the average of a function, we would take our wonderful average equation and just plop in the function instead, multiply it by probability, so on and so forth. We'll actually show a little bit of an example here in a little bit when we start to talk about the wave function. Now, with any collection of data itself, there's bound to be some error or deviation. So let's just say we want to know how much a certain random variable j deviates from the mean, or our average, right? We define this as delta j, and we say that delta j is equal to just j minus the expectation value of j. Now, if we take the mean of the square of delta j, you heard me right, a little bit weird, and Griffith makes some jumps that he doesn't really prove or motivate here, granted. If you want to understand the motivations behind doing this, I do recommend picking up a statistics textbook. There's plenty of them out there online for free. But anyway, if we square delta j here, and then we take its expectation value, we actually get something called the variance. Now, we usually represent this as being lowercase sigma squared, and we set that equal to the expectation value of our random variable squared minus the square of our expectation value of our random variable. It's important because those two things are very different. Now, the variance itself measures essentially how far a set of numbers spreads out from the average value of our ensemble. Taking the square root of the variance gives us the standard deviation, a term that many of you might already be a little bit more familiar with, which describes how much the values of a variable deviate from the mean, right? Now, let's define some other properties for continuous cases now, because we're dealing with waves, not discrete variables, right? If you recall from integral calculus, taking a Riemann sum, right, with certain discrete variables, and then we take our discrete terms and we divide them up into an infinite number of smaller component parts, and then we take this Riemann sum and then we set a limit of this sum to infinity. That essentially just gives us an indefinite integral from negative to positive infinity, or really any other specific domain you actually just want to integrate over. Now, this represents our probability density, and typically you would write this as being, integral negative infinity to infinity of rho x instead of f of x. And because we're integrating over all space, obviously it's equal to 1. Now, for us, we would just simply replace our probability function, rho x or f of x or whatever the heck you want to name your function, with our psi absolute value squared, right? Now, using our earlier definitions, we can define expectation values for a random variable x and a function f of x or psi of x or whatever the heck you want to use, along with the variance of x. Now, at this point, we should explain why we square the absolute value of the wave function. Yes, it took Griffith this long to get to this particular point, and woe on me for writing my script in tandem with the way he decided to teach. This process itself is actually referred to as normalization. We normalize the wave function, as we established earlier, because the wave function itself is a solution to the Schrödinger equation, that ugly mess we showed at the very beginning of the video, right? If it's a solution, then a psi, where a is a complex constant, is also a solution. This is due to the fact that it's a differential equation, and sometimes when you do differential equations, you get constants that fall out. I'll probably find a proof that I have in my notebook, and I will present it here. It's right here, right now, if I can find one. If it's not there, There's probably a funny meme making fun of me right now for being incompetent. But besides the point. To normalize, we just choose an a such that the integral of the squared absolute value of psi over all space would be equal to 1, right? Now, when we normalize, we have to assume that psi is equal to 0, and that we have to also normalize at t equals 0 to ensure that the wave function itself remains valid over all time. Now, using this information, we can calculate new variables related to the wave function. For example, the expectation value of a random variable x is as follows. You have x, or the expectation value of x, is equal to the indefinite integral from negative infinity to infinity, or I should just start saying all space, of x times what is our probability density function, psi of xt to the power of 2, right? This expectation value represents the average of repeated measurements on an ensemble of identically prepared systems, like I was kind of saying earlier. Since the derivative of position is velocity, right, we can take the derivative of the expectation value of position, and taking the derivative of the expectation value of position yields the expectation value of velocity. Funny how that works out, right? It's fun to see little, translations or correspondences. I'm not certain what to call them. Parallelisms between macroscopic physics and quantum physics, because this is where it's about to end. But anyway, now similarly, knowing that momentum also equals mass times velocity, we can also derive the expectation value of momentum as being, mass times our expectation value of velocity, right? Now, there's a standard notation for representing these values mathematically. When we simplify our normalization, we sandwich the operator between the complex conjugate of the wave function and the regular wave function. For example, the expectation value of kinetic energy T equals momentum squared divided by 2m, we would write that our expectation value of t is the integral over all space times the complex conjugate of our wave function times our little operator for kinetic energy times just psi by itself, right? It's just the standard way of writing things, and it actually does make operations with more complex functions down the road a lot easier. To conclude this first very disorganized lesson I've noticed now, here's a very simple relationship between the momentum of a particle and its wavelength, known as the de Broglie wavelength. I said this wrong. I'm very sorry, France. Now, we write this particular relationship as being lambda is equal to Planck's constant h over the momentum p. This, and any sort of organization thereof, will yield any of those properties. So if you have Planck's constant and the wavelength, we can get the momentum. If we have the momentum and the wavelength, we can get Planck's constant every time. It's freaky, but it works out, right? Besides the point, it works. And then also, we have to cover one last thing as well, just a little visualization of the Heisenberg uncertainty principle, because Griffith doesn't really organize his thoughts too well, right? Many of you may have heard about the Heisenberg uncertainty principle coming into this video, but you don't really know what it's referring to. So when we talk about particles, we have to understand that we are dealing with something that normally we treat as being both a wave or a particle, like a photon, right? In this case, we want to look exclusively at the wave properties. When you draw a wave out on a piece of paper, when you're modeling said function, right, you're going to give it its wavelength, it's going to have an amplitude, and it's going to, it's going to stretch out kind of indefinitely as long as you don't change it. Or if you're just modeling said function, it's going to repeat over and over and over again if it's, a nice, easy, like cosine or sine function or whatever, right? Now, let's just say at this point in time, we just selected along our x-axis for location of this particle 1 point, right? Just one. And then we looked at that point, we looked up and we go, what information does this one particular point tell us about the wavelength, about the amplitude of this wave? You're not going to get a whole lot about that. You're just going to notice that it goes up to some point, your output axis rather, and you're going to go, man, it's just 1 point on the wave. That tells me diddly freaking squat, right? Similarly, right, if you say, oh, I want to know more about the wave, you can just expand this area that you're looking at, and then you can get full things like, oh, it's wavelength. Oh, it has this as its amplitude. We can tell X, Y, and Z about it, right? Yes, but there's a trade-off. Where is it? Can you point at any particular spot on this particular diagram and say, with good, sure confidence, that that wave is somewhere there? I mean, obviously you can say, oh, it's probably in between these two particular things, but you can't be totally certain that that wave is exactly there. You're probably actually a little bit wrong, because it could be on the other side of this boundary we've created. So that's what we're trying to talk about whenever we're referring to the Heisenberg uncertainty principle. Mathematically, we represent it like this. We say it is the uncertainty of a particle's position times the uncertainty of its momentum. And the freaky thing about this is that it is always, without fail, greater than or equal to the reduced Planck's constant h bar that I've been referring to earlier, divided by 2. So, in summary, the less we know about a particle's momentum, the less we know about its position, and vice versa. Right? So, anyway, thank you all for listening to me ramble for the past 24 minutes or so. If you have any questions, please let me know. I would love to answer them. If you have a particular problem from these books that you want answered, or from another textbook, I can maybe even make a side video discussing that, walking through some steps, trying to solve these particular problems, so that conceptually they make a little bit more sense. Now, granted, this particular lesson was a little bit disorganized, but in all sincerity, that is probably my fault for not organizing this too well before recording. And secondly, the first chapter in Griffith's is also horribly unorganized and all over the place. He just kind of goes into one topic after the next one, after the next one, after the next one. And I tried to present that information in a similar light, realizing that the first time reading this particular text myself, I had to reread it a few times for it to make a lick of sense and to actually distinguish what topics were what. So, like I said, questions, ask me. I would love to answer them. I'd love to hear from you guys. This is something that I'm very passionate about, and I love being able to share my passions with you and hopefully teach you something along the way. So, with that, thank you all for watching. I will see you guys in the next video.